Okay, so this is the system view. Bismillah ar-Rahman Rahim. And Assalamu alaikum. So let us go with the system view tutorial, the basics of how to use it and to design a RF architecture using the system view. So before we start, so this is the first window that appears when you start the system view and getting started with system view as it says. The upper portion gives you the recently opened workspaces, and the rest are the templates, as for example, the linear template, the digital pre-distortion designer template, and then the RF link template is also there. But we are going to go for the blank for now. By clicking the blank, this schematic appears where you're going to put all your components and the blocks, which you are going to choose it from the part selector on the right. Over here, you can have the RF design as selected, and then you can see all the amplifiers and the lumped and microstrip components, and everything is appearing over here. So let me put it all, and all are going to be appearing. So we can search it from here in order to shortlist any basic component. On the left is the workspace tree, and you have been shown all the design and the data flow, and the graphs are going to also appear over here. You can easily figure it out. You can have multiple designs over here, and all of them are going to be appearing in the workspace tree over here on the left. So in order to start with, I'm going to right click on the design and add some analysis. And in analysis, we are going to for the RF system analysis by adding, yeah, so over here we have paths, calculate, composite spectrum, options. We'll be going through all of them. Level, I'm going to put it 100 minus 100 dB in order to ignore the rest of the spectrum. The outputs, everything can be done, but we'll be going for the for each of them later on. Let me put this maximum order of the harmonics and the intermodulation distortions to be 7 and clicking OK. Now we can have a simple architecture of a transmitter. For example, let we are designing the 2.4 gigahertz transmitter. So for that we need a source, a microwave source. So let me put it multi by clicking multi. This is what is appearing now, multi source. By clicking on it and then clicking here, we have added a multi source. By pressing shift and scrolling up will zoom in, and scrolling down will zoom out. And likewise, you have all these fit selection buttons over here as well. Okay, so we have, let me complete all the components which I have in mind. So after that is going to be the first thing in our design is going to be amplifier. So let me put out an amplifier, a generic one. We can have different parts. If you put it all, we have analog devices and other Skyworks and different vendors amplifiers models available over here, and the components available. You can choose from them as well. We are going for the generic right now. So uh, after the amplifier, yeah. So this amplifier, I need. Sorry, I need a mixer. Uh, so this is the mixer. Putting the mixer and then the oscillator. This is the oscillator. I can put the oscillator over here. Let me place them near so that it is easy for us. We can click and connect like this easily. Okay. So after that, we need a filter, obviously, because we have intermodulation distortions. You see, there are multiple filters appearing over here. Let me choose the Chebyshev filter. Okay. And then obviously the weak signal has to be amplified. So let me put different amplifiers again. Uh, so we have two amplifiers being added over here. Now we can connect them, and here we go with our basic transmitter, a source, and then a mixer, amplification, then a mixer with a local oscillator being attached. RF is coming from here, LO is coming from here, and the IF is here. Um, but in this case, it's not. Yeah. the IF was here, and this is the RF, sorry. It's a transmitter if we consider it to be a transmitter. In the case of receiver, yes, the previous statement was correct. Okay, so putting the output port, we can press out, we can press O, sorry, and you can have the output port appearing over here like this. Okay, so since we have completed it, now we need to specify the parameters of each and every block. So I can put a add and then I can put a wideband source, a CW source. For now, I'm going for the CW source. The center frequency is, for example, 70 megahertz, and over here it is, for example, 30 dBm minus 30 dBm. Okay, and it is appearing over here now. So, okay, now this one I can change the gain, I can change the noise figure. I'll keep it right now like this. I can double click this oscillator block, and the frequency for this, I can change it to through 2330 if I'm aiming for a 2.4 gigahertz. So it is going to have this frequency, for example, and then I can mix it uh, with a mixture of sum type. We have both of them, sum and difference. So summation of 2330 with that of the 70 will give us the 2400, and then obviously we need to put a filter in front of it. For the filter, I keep this to be insertion loss to be 2 or 1.5, the noise figure as is, and then the low frequency is 2395, for example, and then the 2405, 10 megahertz difference. Here I'm going to put it 50 to be more realistic. So here we go. We are done with the basics, basic architecture, and we can now run the analysis. In order to run the analysis, you can double click. Oh, sorry, you can double click over here. Sorry, not this one. Yeah. You can double click and you can see all the source summary is there. The multi-source is the first source, and the power oscillator is the another source. So they are appearing over here. And regarding the paths, we will be talking about it later on. Or let me tell you, the paths are, this is one path starting from port number 1 and going till port number 3. This is one path. And starting from power oscillator and going in this direction is the second path. So for now, we are not choosing them. Let me go with this like this, and let's move on for the simulation. So the uh, in order to run the analysis, the button over here shows the play button. So let me run all the analysis. I hope we are going to have some, yeah, we have some errors. And in order to remove this error, which is actually due to the data analysis that was for the data flow. So we need to remove that data flow to simulate the yeah, the data flow, I guess it is. Yeah, so over here we can simply delete the old data that is for the data flow. It's not the RF analysis, so we need to delete it. Once this is deleted, so then now again we can run the analysis and see if we have any error. We still have error, so let me figure this out how to, yeah, we need to delete this one as well. Okay, now we have no data over here. Let me run the analysis. No, I guess I am deleting any wrong file. Okay, so now you see, yeah, we are done with the analysis. Yeah, so it's done now. I was deleting the file that was not appropriate. So, and that the reason is very simple. It was not the RF system analysis data flow. So it was not RF system analysis. It was a data flow file. So for that data flow, the amplifier, the mixer, the all the components were not supported with that type of the analysis. Now, since we are done with the analysis, now we can simply right-click the output port and we can plot the output power as we can see over here. Uh, Power plot, yeah, here we go. So yeah, so this is the output power at 2.4 gigahertz. As you can see, 2.4 gigahertz is 19.9, which is 20 dBm, and that's pretty much expected, what we actually designed. And because of the filters, the third order harmonics are obviously coming into play, but rest of them are filtered out. And then we have some other intermodes, and but the level is very, very low. You can see it's like minus 38, and it's far away from the operating frequency, obviously. This green line shows the noise figure, which is minus 67.957. So that's the whole design. So we have already designed a power amplifier whose output power, not a power amplifier, sorry. We have designed a RF transmitting RF front end, a transmitter, rather saying transmitter would be more appropriate, with a multi source in the beginning, and we go to the design. So this is the source, and then we are amplifying it. Then we are mixing with the local oscillator frequency. Here is the RF frequency coming out, which is 2.4 gigahertz. And here we are putting the very narrow bandpass filter, and then the amplifier stages in order to get it over here. So if you note, over here it is minus 30, and here minus 30 is brought to a high power level by this amplifier, but then there is a conversion loss over here. So this loss, and then the loss of the filter, and then again the amplification made us able to get a 20 dBm output at the power. Now, in order to check the, what do you call it? The paths over here, in order to check how much each individual component is contributing. So if I click a path over here, it already recognizes the one of the paths. You can clear this one, you can put another path. But let me put it this path, and the 70 megahertz was the initial default single frequency at the beginning of the path, and we are only doing the power measurement. So adding this path and doing the simulations again will obviously now give us an opportunity to see different values over here. You see, desired channel power. So if I click on this desired channel power, now see we have we started with minus 30 as at the source, and then with the 20 dB gain of the amplifier, it boosted the amplification to minus 10. But then we had the mixer with a minus 8 dB of conversion loss, so we are at minus 18. Then we have minus 2 dB of insertion loss of the filter, then we are standing at minus 20 again. Then we added an amplifier of 20 dB, so we are at 0 dBm, and then another 20 dB amplifier. We ended up with 20 dBm signal at. So this graph is really powerful illustration of what each block is contributing to the system in terms of dBm, in terms of power. You can also check the noise figure. You can also check the desired. You can go here again. Sorry. So this is the data of the another data of the analysis we did right now. Going back, so you can have another kind of a graph of accumulated noise figure, noise power, noise figure, and so on. So this shows the noise figure in the transmitter side. Obviously, it is greater And on the receiving side, we are much particular about it. We keep it as low as possible. But over here at the transmitter, yeah, this much is expected, which is being shown as between 6 and 6.5 dB. So it's exactly 6.328 dBs of noise figure. And the contribution of each block is being shown over here. So every block is contributing, and we are ending up with 6.3. So that's it. This is how you use to uh, design a transmitter using a RF chain, and we have done also the chain budget analysis by adding a path. You can add another path over here, and you can do the analysis. Thank you very much.